Recording in progress.
Good morning, everyone. Assalamualaikum warahmatullahi wabarakatuh. First of all, thank you very much to Professor Mabuchi for his time and also for his accept for my students to visit his lab. And today is a final exam for thesis, bachelor thesis of my student, Muhammad Robi Harahap. So in this exam, we have two examiners. First is Professor Mabuchi, and then second one is Dr. Rido, who is also online. And one observer is my student, PhD student, Mr. Edrianto. So again, thank you very much, all of you, to come in this session, this bachelor thesis exam. So Robbie, you have around 15 minutes to give your presentation, and then we will continue to discuss with all of the exam. First, Professor Mabuchi, and then second is Dr. Rido. So please, Robbie, you can start your presentation.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Konnichiwa, good day. First and foremost, let me thank Professor Moji for welcoming us, me and Mahindra, to this beautiful country. We were so thrilled and so happy for the invite, and then for arranging also this meeting room. And thank you for Parido for coming and taking the time of day to observe and also to evaluate. That also goes for Mas Erdi and for Professor Nasruddin. Thank you for being a mentor to me and helping me and guiding me to in doing my research. Okay, so let me introduce myself. My name is Muhammad Robi Harahap. Today I'm going to be presenting about my thesis, the effect of anti-fruit branch biochar mass reaction on the thermoconductivity of PFAD and PKFAD composite phase change material using molecular dynamic simulation. First and foremost, as the growth of renewable energy systems and thermal management application increase, the demand of efficient and also sustainable thermal energy storage materials increase as well. That's why promising technologies are being developed, such as phase change materials. Phase change materials are basically materials that can absorb and also release energy by phase transition. By solidifying, it can release energy, and by melting, it can absorb the energy. And phase change materials are classified by their composition and also by their range of phase change. What we're going to be talking about more seriously is about organic PCM non-paraffin, because there's an abundance amount in this world, and it has high latent heat and it's not flammable. It has also it can also absorb a lot of heat in a narrow temperature range. And for the downsides, it is low in thermal conductivity, about 0.15 to 0.18 watts meter Kelvin. And it also absorbs and releases heat slowly. Okay, so Indonesia is one of the world's largest palm oil producer. It produces over 30 million tons a year, and it contributes to about 59% of global output exclusively. And by producing palm oil, it produces also byproducts, which is PFAD and also PKFAD, which will be the PCM that we're going to be assessing today. And by the addition of biochar, which is specifically EFB, I'm going to further talk about that later, it can increase the thermal conductivity. Okay, from the past research, this was a research done or conducted by one of Professor Nasruddin's students. It is about the effect on adding biochar fraction mass to the increase of thermal conductivity. As you can see, there's PFAD and also PKFAD. Whilst the graph is not linear, but some of them, especially PKFAD, has an increase about 184% thermal conductivity. But although this research is really complete and really thorough, this doesn't demonstrate molecular level mechanism. So we cannot directly observe how individual molecules interact, and that's what I'm trying to do here to understand how this phenomena can work in a molecular scale. Okay, now for the research objectives, we're going to make it quick. So I'm going to try and model PFAD and also PKFAD, also biochar composite, using MD simulations. And I'm trying to validate what force field I should use with respect to density. And then I'm trying to evaluate adding biochar by a fraction of 5, 10, 15, 20 to 40. And then I'm going to analyze microscopic mechanisms using radial distribution function for thermal improvement and compare MD simulation from the experimental data to my simulation data. And then for the key hypothesis, should be the EFB biochar addition will increase PFAD and PFAD thermal conductivity. And higher mass fraction tends to increase thermal conductivity. And PFAD versus PKFAD will respond differently due to its different composition and also chains. Okay, now let's talk about what MD is. So molecular dynamic simulation is basically a simulation method that tries to predict how a molecule moves and how it interacts and how it affects properties like thermophysical or mechanical. There are three main components. When we're first solvating a molecule, we get the initial atom or the initial amount of atom. And then there are three components that we know, which is initial position, velocity, and also interatomic energy. Interatomic energy, there are bonded and non-bonded, but let's focus more on non-bonded. There is something called Coulombic interactions, which are interaction that happens through molecules that have charges. And then it tends to repulse and also attract depending on their charges. And then there are van der Waals. It is exclusively attractive motion. That's why we have a negative over there. And then electronic repulsion, which is exclusively repulsion. That's why it's noted as positive. And then there's something called Lennard-Jones energy, which can be seen here. So Lennard-Jones is basically a combination of van der Waals and also electronic repulsion, where if they're made into a graph, this is the electronic repulsion, and this is the van der Waals. And then when you combine it, you get a graph something like that. And getting the graph, maybe you can notice that there is a slight dip located in R0. That dip is the equilibrium point where the most minimum energy is found. Okay, and then by knowing what the energy is, you can calculate the force. The force is basically the first derivative of energy. Okay, and then once you get the force, we can calculate the acceleration by using Newton's law of motion. And then by that, knowing the acceleration, we can calculate the position, velocity, and also energy with a small increment of time. Okay. Okay, now talking about the processes now, but in theory, energy minimization is one of the first processes that we do in the simulation. So energy minimization is a process of finding an arrangement in space of a collection of atoms. So basically it tries to find the smallest energy possible for a system so once we first solve a system, the system is still artificial. It still has some particles that are overlapping one in each other. So energy minimization tries to fill that gap and create an equilibrium. Okay, so what we're trying to find is net interatomic force close to zero. To find so basically energy minimization is the lowest possible energy in this graph. So this is the graph of potential energy with respect to distance. Okay, so first we need to find the stationary point over there. The stationary point is basically these points, the most bottom point or the highest point. It's done by deriving the energy graph, and then by deriving it twice, or the second derivative, you can find out if it's minimum local or maximum local. This is the local energy minimum, this is the maximum local energy minimum. Okay, that's for one dimension. For three dimension, it's basically the same, but you have to do it in partial derivatives. Okay. Okay. Another step is called annealing. So after energy minimization, let's say your molecules now are in this state, are in the local minimum. So what annealing tries to do is it's trying to heat the system in a controlled way where it can increase the temperature and also therefore increase the kinetic energy, and in turn hopefully get the molecules or the system to go and pass the local barrier, which is denoted as B there, and hopefully achieve global energy minimum. Okay, for equilibration, so after minimization, heating, or annealing, the system still shows fluctuations in temperature, density, energy, molecular structure. So equilibration basically tries to allow the system to stabilize under a controlled manner or a controlled simulation condition. So usually we're going to use NPT, which is an ensemble, and it controls the variable of N, which is the amount of atoms, P, which is pressure, and T, which is temperature. And then by doing that, it ensures the system has adjusted properly to the simulation conditions. Okay, okay, now for production, this is a bit advanced, but I'm going to be using RNEMD, which is reverse non-equilibrium molecular dynamics, for my thermal conductivity production. So production is basically when the system is already stable, but the data needs to be produced and it needs to be collected for analysis. So the data here being thermal conductivity, there are different methods. EMD is one of them. It is basically when you're in an equilibrium state, you don't give it heat transfer, you don't give it temperature gradient, you don't give it external heat, and basically how it does is that how it calculates thermal conductivity is by something called Green-Kubo. It's basically when you plot a graph called autocorrelation function, and you can see even in an equilibrium state, the graph is still fluctuative, and it contains properties such as properties that you can extract, one of them being thermal conductivity. And then NEMD, or non-equilibrium, it is basically you trigger something, this being temperature gradient. So you make a reservoir, a hot reservoir and a cold reservoir, and hopefully it can calculate the heat flux. And then for my simulation, we're going to use RNEMD, which is the reverse of NEMD. It basically, instead of creating a temperature gradient, it creates a heat flux, and then hopefully it creates a temperature gradient. So this heat flux is created by switching kinetic energy from one atom to another atom. For my simulation, every 500 time steps, or every 500 steps, we switch kinetic energy from atom to atom. Okay, so the total energy kinetic can be calculated using that, and then it is corresponding to the heat, and then by the heat you can calculate the heat flux, and then you can calculate the conductivity. Okay, and now let's talk about material. What I'm going to be using is BioPCM thermal energy storage material. One of them is PKFAD, one is PFAD. So basically, it's made out of crude palm oil, and then it produces palm oil and palm stearing and something like that. But from the steps, deodorization, we can get PFAD. So it's basically a byproduct, and it's dominated by long chain fatty acids, which are ranging around 12 to 16 carbon chains. And then for palm kernel fatty acids, it's made out of palm kernel oil, and it's dominated by medium chain fatty acids. What's what can we get? What's the key takeaway? So the key takeaway is PKFAD being a medium chain, it has a lower melting temperature, which means that it has a lower operating temperature. Because if we're talking about PCMs, melting temperature is automatically operating temperature because we need it to solidify and melt, solidify and melt. So PKFAD, due to its smaller melting temperature, it's used more for room temperature, which is building thermal management and thermal energy storage system. Okay, now let's try to solve it, the composite phase change material. So the composite phase change material, there are several. There are different references that I used for the compositions for each and every material. So this one is from Siti Fatima Abdul Halim, and using and it's over here, and using fraction mass calculations, we can get the corresponding amount of free fatty acids to create the PCMs. And why did I use 500 molecules to simulate the PCM? Because lower than this, you cannot put this one linoleic acid into the mix because it's too low, the amount of molecules. Okay, the same goes for PKFAD. Let's just go right into that. Okay, now let's talk about biochar. So biochar is basically a high carbon content material with a lot of pores. So if you look here at the graph, biochar is made by biomass. So biomass like manure, compost, organic waste. But what we're trying to look more into is empty fruit bunches. So we're going to use that as a 100% source of carbon, which we're going to pyrolysis. So pyrolysis is basically a method that happens in a reactor, and in this reactor you're controlling the temperature, increasing it gradually, and in a controlled oxygen state. So then you can get biofuel, and you can also get biochar. Biochar is usually used for putting it into the soil, and it can make your soil more stable, remain in soil for a long time, and also improve soil structure. Okay, now this is the interesting part. So biochar has a lot of groups, or gugus fungsi, a lot of groups. So what we're interested about is the carboxyl, carbonyl, and also hydroxyl. So from these groups are categorized as polar. So polar means that like here in carbonyl, C and also H, they have a difference in charges, which O is relatively more electronegative. So it tries to pull electron more, which makes it more negative, while C is more positive. So this difference in charges creates a polar. The key takeaway is polar groups will interact really good with other polar groups, which we can see later. Okay, now I've also made my biochar molecule, and then I made it and I validated it with the molecular weight and also with the molecular formula. And then, yeah, that was it. Okay, now I'm going to discuss about the validation methodology. So I'm probably going to make this kind of quick, because after this there is another methodology, which is a production methodology, which is more compact and volatile. So first, after we've made the molecules in pre-processing, we're going to do the MD simulation. So basically, first we're going to minimize the energy after we've made the molecules. It has a high energy because molecules are overlapping one in another. And then after energy minimization, it is done in 300 kelvins. We're going to do annealing. So this is done using NVT. So we're controlling the temperature using Nose-Hoover thermostat from 300 to 380. Okay, this is for us to be able to get a global minimum in general, and then we're going to do cooling to put it down, to decrease the temperature, so we can eventually do equilibration and also production. Okay, so what are we trying to produce in this simulation? So we're trying to produce density. Obviously, we're trying to get the average amount of density, and we're going to see if the density is similar to the one that is in our reference. So our reference density for PFAD that is in liquid form is 0.85 to 0.87, which is averaged to be 0.86, and I varied the force fields amongst 4 force fields that are native to WinMOSTAR, which is OPLS-AA, UFF, JFF, and JFF2. So although UFF is a universal force field, it is not catered to any organic material whatsoever. But OPLS, AA, and JFF and JFF2 are catered and are tailored to what we're trying to do, which is organic material. Although OPLS is more liquid, but yeah. So as you can see, the errors are not that far, but but the lowest one, what we're going to use is JFF2. So beforehand, maybe a little bit background, I used the assigned charges method using AM1BCC, but after further evaluation from Professor Mabuchi, I used RESP. So after I researched a little bit about RESP, it basically is good for my simulation because my simulation consists of electronegativity, particles, and then polar groups. That's why RESP is known for calculating using quantum mechanics. Yeah. Okay, this is for the thermoconductivity production. Okay, so after we've made our system, and then we're going to energy minimize. So we're going to find the lowest possible minimum energy possible. What dictates our energy minimization to stop? I've put an array of things that would stop my simulation, which is the relativity. If the relativity energy is smaller than 10 to the power of minus 4, and then if the force norm is smaller than 5 times 10 to the power of minus 3, and if it reaches 10,000 iterations, it would automatically stop. And then annealing. For annealing, from a stable geometry that from energy minimization, a stable geometry, we give it an initial velocity. This initial velocity we use using a distribution called Maxwell-Boltzmann, and then we alter the temperature from 280 to 380, and then we use something called the Gnauss-Huber thermostat. And then what it does is basically it melts and it rearranges artificial configuration from the solvating phase. Okay, and then a pre-equilibration, we're going to use NPT. So it basically, after annealing, it becomes liquid, and then it brings the liquid to a stable condition again after you increase the temperature while annealing. The kinetic energy is a bit too high for production, so we decrease the temperature, and then we set the pressure to 1 atmosphere, and we wait until the volume equilibrates and also the density equilibrates. Hence the name pre-equilibration. And for the equilibration itself, it's basically the same thing, but we're doing it for every temperature from 300 to 350. Okay. Okay, so after the production using our NEMD, we get these graphs. The top graph is the experimental data from my colleague back in Indonesia, and the bottom one is my simulation data. So the y-axis on the right side is the thermoconductivity value, and then the y-axis on the left side, indicated by the color red, is the increase of conductivity. Okay, and then the x-axis is the addition of biochar content. Okay, so as you can see, although the values are not particularly the same, not exact, but a wise man once said that molecular dynamics is not used to make the simulation exactly the same, but we're trying to find out what phenomena is behind what's behind the phenomena in a molecular scale. Okay, so it in the 5% and 10% it increases, and then it decreases significantly in the 15%, and then yeah. But for my simulation, the most increase that it experiences is 29.7%. Yeah, we're going to assess more on the microscopic analysis. Okay, and for this one, the experimental data shows that there's a 184% increase in the 5% addition of biochar, and then it gradually decreased until 0.26. For my simulation, it's not exactly the same, but it experienced a 100% increase, and then it decreased even below the initial value without the addition of biochar. It decreases below that, and we're gonna try and explain it later. Oh, maybe I explain it now. So after further analysis, the more amount of biochar added, which is in this context 50%, the capability of phase change material to absorb and also release heat as a latent heat storage device decreases because there are too much biochar and there's less of phase change material to do its thing. Later we're going to discuss more. Okay, so before going to the analysis, which is radial distribution function, I'm going to explain about the mechanisms of heat transfer in PCMs. So first of all, what is nano-PCM? So nano-PCMs is basically composite phase change material that are added with nano-additive material. How to do this? By dispersing nano-sized solid particles into PCM matrix. So by doing this, the thermophysical properties such as thermoconductivity will increase, but without sacrificing latent heat storage capacity. Okay, so there are two main components of nano-CPCMs. The first one being PCM matrix, right? Which is a media for latent heat storage, and the second one is conductive additive, which here is biochar. It fixes the thermal pathway, which we would discuss here. Okay, so so the first mechanism that we're going to talk about in organic phase change material regarding heat transfer is phonon. So maybe contrary to popular belief, the thermoconductivity of the propagation of heat in a phase change material is using electron, but that is wrong. It is actually using phonon. So phonon is basically a quantized vibration that of an atomic or a molecular material, and it moves through the lattice of atomic and molecule, and it transports thermal energy through material. Okay, so basically without biochar, pure PCMs have high resistance because it has an irregular molecular structure and it has a weak bond. So the effects of adding biochar, it has a higher phonon propagation effect, and also it decreases, and also phonon scattering decreases because biochar is more conductive. Okay, more interesting is percolation. So percolation is basically the formation of continuous networks of biochar touching each other, which creates a thermal pathway. So this thermal pathway is basically a mean-free path for thermal energy to cross, and but this you need to have the amount of biochar has to be above percolation threshold to have an effect. Okay, lastly is Brown motion. So Brown motion, as the picture depicts, it's basically a random movement. Here it happens in the liquid phase of phase change material. Microscopic particles of PCMs crash into another, and also in turn crash into the biochar, which mixes microscopically and helps with distributing energy and increases diffusivity. Okay, lastly is the radial distributed function analysis. So what is RDF? RDF is basically denoted as GR. So GR describes the probability of finding a particle at a distance of r of a reference particle. So let's say what we're trying to assess is the particle here. Let's say this is O from PCM, oxygen from PCM, and then we're trying to find what's the possibility we can find the hydrogen from biochar. So we use this radial distribution function, and then we can find 1, 2, and 3 amounts of hydrogen from biochar. Okay, so basically density isn't also always homogenic. It is different in one place and another. So this tries to find where's the most dense and where's the least dense area with respect to distance. Okay, and then this is what we're trying to assess. So this is from PFAD. This is also a graph of PFAD. First, we're going to analyze about PFAD. So PFAD has several groups that are polar, which will interact really good with biochar. The first one is carboxyl group. So carboxyl group consists of carbonyl and also hydroxyl, CO and also OH, which both are polar. And then let's see the effect here. So here we can see that the first peak is R in between 2.7 to 2.8. This indicates a strong short-range reaction. So from a distance 2.7 to 2.8, there are a lot of biochar atoms or biochar molecules, and it is consistent from all PFAD addition, and the highest peak is at 5% biochar. So what does this mean? So if we look back at our previous graph, the thermal conductivity is highest in 5%. What this means is the more dense biochar is around the oxygen in carbonyl PFAD, the more dense it forms a thermal pathway, and there is denser contact between biochar and also PFAD, which in turn reduces thermal resistance, and it increases vibration, which propagates thermal heat easier through PFAD. This also happens here. There is in between below 2 and also 2, there is a first peak which is made by PFAD plus 5%, and there's another peak, a second peak in the distance of 4 angstroms, also by PFAD 5. And looking at the thermal conductivity graph, it makes the same trend, and then PFAD 15 is also lower, and PFAD 14 is the lowest. Okay, maybe let's. Okay, so this is the analysis for PKFAD. Something similar, but in PKFAD, the polar groups are carboxylate and kalium. Those are polar, so these will interact really good with biochar. Okay, so looking at the graph, the same thing goes. PKFAD pure is down here, and pure is also down here because we cannot see biochar molecules if the PFAD doesn't contain biochar. And then PKFAD 5% is the highest. Same goes with this one at roughly the same distance, and this also correlates really well with the thermal conductivity graph. Okay. So this is the conclusion for my presentation today. So firstly, before we found out the error relative to the experimental PFAD data for force fields, for GAFF2 was selected because it has the smallest error possible, which is 1.66%, and then the addition of biochar affected the thermal conductivity of both PCMs, with the highest thermal conductivity in both systems was obtained with 5% addition of biochar, and then indicating that this is an optimum composition. Higher fractions such as 15, also 40, tended to reduce the improvement, due to biochar agglomeration, which decreased the effective interfacial contact area. And then RDF analysis showed that 5% systems had stronger polar and ionic interactions between active PCM groups. These interactions reduced thermal boundary resistance and supported thermoconductivity enhancement. And then the last one is the different molecular composition, PFAD and PFAD, cause different thermal responses to biochar addition. We can see that from the graph. They both have two different trends. Overall, the molecular dynamics results were consistent with experimental trends and can explain the microscopic mechanism of thermoconductivity enhancement. Maybe that's all that I can talk about today. Thank you so very much for listening. Assalamualaikum warahmatullahi wabarakatuh.
Okay, Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Robbie, for a nice presentation. And now, discussion session. So please, Professor Mabuchi, to give a question to the Robbie. Thank you. Please.
Oh, okay. Thank you very much for your nice talk. I think, yeah, I looked through your thesis and it looks like, yeah, your thesis is very well structured and your objective is clear, and the story was quite easy to follow, so, which is a good thing, right? So that's a, yeah, very nice topic. My first question is, yeah, like you said, so when you compare the thermal conductivity with the experimental data, yeah, as you said, yeah, although it's not the perfect, right, reproductions, but our intention is to understand the phenomenon behind. So yeah, I totally agree with that. So yeah, sorry, yeah, with you one. And yeah, and then it was very interesting to see that, especially for PKFAD,
Yes.
there's a high peak, and then you also kind of like reproduce the peak of the thermal conductivity. And can you explain again why they have thermal conductivity improvements with a small amount of biochar, and why they decrease if you add more?
Okay.
Right, yeah.
So
I'm not arguing about the trend. I agree that the trend is okay.
The reason.
Yeah, reason.
So based on my analysis, maybe there are a few. Maybe the first one being that these are two different PCMs, right? We're talking about PFAD and PKFAD. Maybe the capabilities of the PCM to store energy are different. Maybe PKFAD maybe if you decrease PKFAD by a lot, it doesn't have the same amount of capabilities to absorb and release. So that's why if you increase the biochar, which in turn decreases the amount of PCM, that's why the PCM effect doesn't, the PCM effect decreasing in turn decreases also the thermal conductivity.
Okay, thank you. This is the general questions. So, and which is most important. So your target was like, you know, you want to, well, maybe you want to further improve the thermal conductivity, right?
Yeah. Yes.
So based on your simulation results, do you have any suggestions on like how you could improve further for the thermal conductivity? Like maybe mixing, I don't know, PKFAD with PFAD or something else? Like, do you have any suggestions or expectations?
Maybe because our limitation in this research is trying to maximally use the biochar that is basically waste in Indonesia, that we produce most in Indonesia. That's why we are limited to this choice of biochar. And in my opinion, a lot more biochar there that are mostly used in soil that probably has better thermophysical or mechanical properties. Yeah, maybe by changing the biochar itself.
So you
Actual-
say like many types of biochars that exist.
Yeah, basically from manure or from compost or from some.
Okay. Which gives you a different results.
Yes.
Oh, okay. That's interesting. Thank you. Thank you very much. Yeah, that's all for me.
Thanks so much for
Yeah.
Thank you, Professor Mabuchi, for this question. And next is Dr. Rido. It's now your turn.
Thank you, Prof. Nasruddin. Thank you, Robbie. Good. I think it's already almost lunchtime. So, how are you, Professor Mabuchi?
Good. How are you? Nice to meet you.
Good, good. Nice to meet you again. So, it's been a while. Robbie,
Yes.
I have one question regarding the thermal conductivity.
Okay.
Why is it having an optimum value at 5%, not 40%?
Ah, okay.
I mean, by law, the
Mhm.
more weight you add, the higher the thermal conductivity should be, theoretically.
Mhm.
If you see the equations for thermal conductivity of two substance, let's say if you create a nanofluids or nanolubricants, the higher the weight fractions, the higher the thermal conductivity should be. But the fact that we are finding shows that the maximum is at 5% and then it decrease rapidly as the fractions get higher. How do you explain this?
Yes. Maybe I would result in my previous thinking, which was maybe you can contradict this, but for now maybe my reasoning would be that there are two main compositions in nano composite phase change material. The first one and second one are equally important. The first one being the PCM itself, which functions as a latent heat storage device, and then the second one being the biochar. The biochar is basically an additive that can fix the thermal pathway of the system, so the heat can transfer better, and it's more conductive. But maybe with the increase of biochar and also the somewhat decrease of density in PCM, the effect of latent heat storage that was caused by PCM would also in turn decrease. So if you have more biochar, in this case 40%, and the PCM goes really low, there are no more heat to store in the system. Maybe, maybe I don't know, maybe I don't know.
Okay, yeah, that's interesting. I mean, you can compare it with a classical model. Also, try to explain the deviations between the classical models and your findings. I think that will be a good addition to your thesis also. And so we know that ECM works based on latent heat, right?
Yes.
And you add this nanoparticle to the PCM.
Yes.
So will it in fact affecting the latent heat of the combination between the, if we combine the PCM and this nanobiochar, will they affect the latent heat of these combinations? For example, will it have a higher temperature for the phase to change? from solid to liquid? Does it require more heat than if we add PCM, if we add nanoparticles into the PCM?
So actually, by the curiosity of me, I've actually made a graph, but I didn't put it here. But it's essentially the temperature profile between each biochar fraction. So it was concluded that there wasn't a particular the temperature of change of phase change from fluid to solid did in fact change. Was in fact not the same from the lower percentage to the higher percentage. But I forgot the specifics. But yeah, there was an effect in the whole composition as a whole. I think that's.
So, Happy, you give these molecular dynamic simulations, right?
Yes.
Have you checked whether if you run it repetitively, will they have a similar result, or this is just to check the accuracy of your model?
Yeah. Yeah, that was one of my considerations doing this research. I wanted to. I put it in one of my drafts, my thesis drafts, that I wanted to, for every variation, for every simulation that I did, I wanted to minimum 3 simulations per variation. But due to the errors that I did, the simulations that were error, and it took a long time, and for every simulation it took like 1 or 2 days. Yeah, I couldn't achieve what I wanted to do in the first place. Yeah, so
Okay.
maybe for the further I can improve.
Okay, yeah, that's a good notes to add into your thesis, into the suggestion part,
Yes.
just to check whether the models that you develop are or can predict the properties of the nano PCM, so to say, accurately.
Yes. Thank you so much.
I think that's all from me, Prof. Nasruddin.
Okay,
I hand
thank
it
you.
back to you.
Yeah, thank you, Dr. Ridho, for the question. And is there any question from Professor Mabuchi?
No, I don't have further questions. I'm fine.
Okay.
Yeah, I'm good.
Okay, thank you. So I think, Robbie, you can make a note all of this question and discussion to improve your thesis book, and then you can submit later. So I think this topic is very interesting, because it's talk about PCM. PCM alone is very special material, and then because you combine with latent heat inside this material, and then you add something new to increase the conductive properties, but it's not always increased, because the combination between PCM and conductive material is not so always linear trend. So that's why very interesting if we can analyze why this phenomenon is appear in this mix between PCM and additional conductive material. So maybe a molecular dynamic simulation can explain better why this phenomenon happened. So that's why I think in the future also it's very interesting to know more deep about this material and the properties. So again, thank you very much, Robbie, for the nice presentation, and then Professor Mabuchi for the time and for the review this topic, and Dr. Ridho, and then also Erdi, and Mahen is an assistant for this presentation. Thank you very much. So I think we can close this session, and thank you again. Have a nice day. Assalamualaikum and good afternoon.